It's time for one of my favorite sections in algebra. The reason why I like it is because it can be challenging, but at the same time, it's kind of fun to see that you can do all kinds of things with these radicals to simplify them. So basically, we're going to simplify radical expressions. So we're going to take a square root of something, and we're going to get it in its simplest form. And to do this, we have to follow three rules, three conditions. Okay, we're going to talk about each of these individually. Our first condition is that no radicands, that's the number inside the square root, no radicands have perfect square factors other than 1. That's going to be the first thing we're going to look at. Okay, I'm going to use that word a lot. Perfect square factors. I'm going to use those three words. Perfect square factors. Okay, so we got to get used to those. Our next condition is no radicands contain fractions. So if there's a fraction inside your square root, we can simplify that. So we can't leave a fraction inside the square root. And we'll talk about that one. And lastly, no radicals appear in the denominator of a fraction. So if I have a radical in the denominator, I got to get it out of the denominator. Okay, we don't like that in the denominator. And we'll show you how to do that. So first things first, we have the product property of square roots. So if I'm multiplying inside my square roots, I can split up my square root bar. I can take the square root of 4 times the square root of 9. I can't do this with addition and subtraction. Some people are going to try to do this someday, and they think they can do this, and they can split that up. You can't do that, okay? You cannot do that with addition and subtraction. Just multiplication, and we'll find out division as well. Because if I look at this, square root of 4 is 2, square root of 9 is 3, and that equals 6. And I can check my work here because really I'm supposed to do what's inside parentheses or inside brackets first. So I should do that 4 times 9, which is 36, and the square root of 36 is 6. Well, that's not what I was writing. And those match up, right? 6 and 6. So it works. So I'm able to split my square root bar up when there's multiplication. And this is going to help us when we simplify our radicals now, when we want to simplify them. So what I want to look for to be able to simplify are perfect square factors. Well, factors are numbers you multiply. So if I think about factors of 52, for example, and I got 1 times 52, I got 2 times 26. Let's see, 3 doesn't go into there. Does 4 go into there? I got 4 times 13. And I think that is about it. Okay, so those are my factors of 52. So I want to look for perfect square factors. Well, perfect squares are what? 1, 4, 9, 16, 25, 36, right? So on and so forth. It's numbers we can take the square root and get a whole number, right? Square root of 4 is 2, square root of 9 is 3, square root of 16 is 4. So if I look here, 4 is my perfect square factor. So I want to break 52 into 4 times 13. I want to use that. So I'm going to break square root of 52 in 4 times 13. Because I can break this up. I can take the square root of 4 times the square root of 13, just what we talked about. And the square root of 4 is 2, so now I can write 2 times the square root of 13, which is my simplified form. Okay? If I took the square root of 13, I'm going to get a never-ending decimal. And if I round it, I'm not exact anymore. So this is an exact answer. This is 2 times the square root of 13. That's an exact answer. If I take that out of the calculator and round, now I'm approximating it. And I want to be exact. Okay? And the quick way I usually do this is I'll think about my perfect square factors. I'm like, 4 times 13. And the square root of 4 is 2. The square root of 13 I can't do. That's kind of my quick way to do it. I'll just write the my factors that contain the perfect square factor right below it. Okay? If you want to show all your work, that's awesome. Some people need to see that they're following that rule, but you can also do it the quicker version here. Okay, let's look at one with a little bit bigger number inside the radical. A few perfect square factors, okay? And this will make a difference on which one you pick. So if I think about 180, 4 goes into it, 4 times 45. So that's something I could choose. I believe 9 also goes into it, 9 times 20. And believe it or not, 36 goes into it. 36 times 5. So if you think about it, if I choose the biggest perfect square factor, let's just walk through it. So I break 180 into 36 times 5, and the square root of 36 is 6, and I leave the square root of 5. It's already simplified. Okay? If I end up picking one of the other ones, for example, 4 and 45, a lot of people do that because they'll think, oh, 4 goes into it, and they'll see 4 times 45. So if I break square root of 180 into 4 times 45, well, the square root of 4 is 2, and the square root of 45 is not simplified. It still has perfect square factors. 9 times 5, right? So I could break 45 into 9 times 5, and I get square root of 9 is 3. So when I bring that out, I need to multiply it still, and the square root of 5. So 2 times 3 gives me 6 times the square root of 5. I still get the same answer. Okay, but I'm just going to have to simplify one extra time because I didn't pick the biggest perfect square factor, which is totally fine either way. Okay, sometimes you don't want to waste time looking at all the factors of 180, so you might just use 4 times 45 and go with it, but it's completely up to you. And lastly, if they have two radicals split up, it's your choice. I can either find perfect square factors of 24, for example 4 times 6, and simplify from there. Or what I usually do is I combine these two right away. I'll take the square root of 2 times the square root of 24, and I'll write it as the square root of 2 times 24, which is the square root of 48. And then I'll find perfect square factors to that. I think that's easier for me. And a perfect square factor of 48 is also 4. And I believe something else. 16 is even bigger, isn't it? I can go 16 times 3. So I take the square root of 16, which is 4, and the square root of 3, and I'm done. Okay. And if I would have picked 4 times 12, I would have to have broken up the square root of 12 into 4 times 3. Okay, so it just depends on what perfect square factors you use on how many times you have to simplify. But we just want what's inside the radical to not have any perfect square factors anymore. Okay, the tough part comes when we look at variables with exponents. Okay, if I look at this first one, square root of x, this is already simplified. I can't do anything with that. Okay? If I think about the square root of x squared, well, squaring and square rooting are inverses, so they kind of cancel each other. So I think this should be that. It should be x. The square root of x squared is x. And let's test something once. Let's test the number 3, for example. So we're saying 3 squared equals 3. If I plug in the 3 for x. Well, is that true? 3 squared is 9. The square root of 9 is 3. Good. That works. Okay? Well, what if I tried a negative 3? I'm going to plug a negative 3 in for x. Well, negative 3 times negative 3 is 9, so that works. I can do that. But is the square root of 9 negative 3? It is not. Okay? It doesn't work. So the square root of x squared is not just x, okay, because I can't use any number for x, but it's the absolute value of x, okay, because I could put a negative 3 in there, but I need it to be a positive 3, don't I? I need it to be a positive 3. So you have to have, because that would make this a positive 3, which works. So I have to have absolute value bars around that when I do that. Okay, that's the kind of trick here. If I look at this next one, as long as I can get an x squared, I know that is going to give me the absolute value of x. So I'm going to break this x cubed into an x squared times x. I just pulled out one of the x's. And I know that the absolute value of x squared is, the square root of x squared is the absolute value of x. And I still have the square root of x there. Okay, looking at the square root of x to the 4th. Okay, now I'm thinking it's going to be x squared. Kind of cuts that exponent in half. But do I need absolute value bars or not, like I did before? Well, let's test 3 out again. Let's test 3. We can do that. So the square root of 3 to the 4th equals 3 squared. Well, 3 to the 4th power is 81. The square root of 81 is 9. That works out, okay? Well, let's try a negative 3 now. Square root of negative 3 to the 4th equals negative 3 squared. Well, negative 3 to the 4th is 81, and negative 3 squared is 9. Square root of 81 is 9. So it works. Okay? The reason why it works is because I have an even exponent. So if I plug in a negative number for x, any negative times itself is going to give you a positive, just like it did here with 9, right? Negative 3 times negative 3. So I don't need absolute value bars when I have a positive exponent after I take the square root. Okay, so I can just leave this as x squared. So looking at the next one, get it to an even exponent underneath. So I'm going to break it into x to the fourth times x. And x to the fourth is, square root of x to the fourth is x squared times the square root of x. So let's keep going here. Well, I can just cut this in half, x to the third, but it's an odd exponent. So what do you think we're going to need around it? Right? This was an odd exponent up here. So we needed absolute value bars. So it's really the absolute value of x to the third. Same with this next one. Rewrite this as x to the sixth times x. And the square root of x to the sixth is absolute value of x to the third times the square root of x. I can't simplify that. And the last one is just x to the fourth. It's a positive exponent, so I don't need absolute value bars. So if it has an odd exponent, so for example, my 1, my 3, I need absolute value bars around it after I take the square root. If it has an even exponent, I don't need it. Okay, so let's take a look at an example. I know some of you are probably confused out of your mind right now. So right here, I'm going to take the square root of 45 times a to the 4th times b to the 5th times c to the 6th. So let's start with my number right away. Perfect square factors of 45, 9 times 5. And I know the square root of 9 is 3. I'm going to write all this out so we don't confuse it. So what I can do here is I can break this off. I can take the square root of 45 times the square root of a to the 4th times the square root of b to the 5th times the square root of c to the 6th. Some of you are going to be able to skip this step, but it's good to see this right away. Well, like I said, 9 times 5 for the square root of 45. So I have 3 times the square root of 5. Okay? And then I have square root of a to the 4th is a to the 2nd. Okay, so times a to the 2nd. And then I can break this into b to the 4th times b. B to the 4th times b. Well, square root of b to the 4th is b to the 2nd. And I still have that b inside the square root. And lastly, square root of c to the 6th is c to the 3rd. But since it has an odd exponent, I need absolute value bars around it. Well, now I want to put everything that's not in a square root out front, and everything that's inside a square root inside the square root. Because it's all multiplication. I can combine all these things. So I'm going to put my number, my 3, that's outside the square root. Then I'm going to go a squared, b squared, right? Pick those two, and absolute value of c to the 3rd. And then I put everything else that's into the square root. 5b. Those are my 2 square roots. So I can combine those. So this is my simplified form. That's my simplified form. I know it gets kind of confusing. Once you learn the shortcut way here, like I like to try to do, I think it takes some of the confusion away. So what I usually do is I just work part by part. So I take 45. Well, 9 times 5. Okay, and I know the square root of 9 is 3. So I know that's going to be out front. Okay, so I know that part's gone. Square root of a to the 4th, I know is a to the 2nd. So that's going to be done. And then the b to the 5th I can rewrite as b to the 4th times b. And square root of b to the 4th is b to the 2nd. So I know that's going to be out front. And I'm still going to have that b inside. And the square root of c to the 6th is c to the 3rd, but it has an odd exponent, so I need absolute value bars. And then I just leave what's left under the square root, that 5 and that b. So that's kind of how I do it the shortcut way. I just take it part by part. So whatever's best for you, if you like to write it all out, like I did in this first step, to be able to keep track of everything, or if you can, come up with your own method with your shortcut, I kind of like doing that. Okay, we also have a quotient property for it, so I can actually break up my square root for division, just like I did multiplication. So I can take the square root of a over the square root of b. I can break that square root bar. But the key is here, I don't want a square root in the denominator. Okay? So to get rid of a square root in the denominator, I have to multiply it by itself. I'll show you what I mean. So this top one up here, I want to get rid of this square root of b down here. I want to get rid of that square root. Can't have a square root. Well, this might be easier if I look at our first example. Use some actual numbers here. So I can split this up. Square root of 45 over the square root of 10. Okay, don't turn that into a decimal or anything like that. Leave them like in the fraction form. Well, to get rid of that square root of 10, to get rid of that square root, I'm going to multiply. I got to multiply by 1 all the time because I can't change the value of it. Well, to get rid of that square root down there, I need to multiply by the square root of 10. Just multiply by what it is. Because the square root of 10 times the square root of the 10 is just 10, right? Because it's the square root of 100. But what do I need to put up top? Well, what I said is this really needs to be 1, isn't it? So it needs to be the square root of 10, right? Because I got to multiply by 1 so it doesn't change the value. So if I look down below, it's going to be 10, just like we talked about. And remember, multiplication with square roots, I can just multiply what's inside the radical. So 45 times 10 is 450, so I really have the square root of 450. Okay, but now I should see if I can simplify that 450. Well, the first one off the top of my head I can think of is 25. So 25 times 18. But if I notice 18, I can still break up 2. So there's got to be a bigger perfect square. And it happens to be 225. 225 times 2. Because the square root of 225 is 15. Okay, so I'm going to write this down below here. So the square root of 450, I'm going to rewrite as square root of 225 times 2 over 10. And the square root of 225 is 15. And I still have the square root of 2. Well, I can actually simplify my 15 over 10, can't I? A 5 goes into both. 5 goes into here 3 times. 5 goes into there twice. So I really have 3 times the square root of 2 over 2. So crazy. Who would have thought my original problem, square root of 45 over 10, would simplify into that? That's what it is in simplified radical form. Okay, it just takes a little. Last problem, same type of thing. I got to get rid of the radical in the denominator. So I'm going to multiply it by itself. Well, and I got to do that on top as well because I got to multiply by 1 essentially. And so we get the square root of 24n, right? Because 3 times 8 over 8. Okay, because 8 times square root of 8 is 8. And perfect square factors of 24 would be what? 4 times 6. So I'm going to break that up into 4 times 6 here. And the square root of 4 is 2. Can't do the square root of 6, so I leave that 6n inside of there. Over 8. And if I look what's on the outside of the radical, I have a 2 and an 8. They both have a 2 that can go into there once and 4 times. So we end up with 1 times the square root of 6n. I don't need to write that 1 over 4. Simplify. And I can't simplify the 6 and the 4 together because the 6 is inside the radical. So that is in simplified radical form. So looking at up at top of my example, I would have multiplied by the square root of b over the square root of b. And I would have ended up with the square root of ab over b. Okay, that's how that would have worked. And the last thing, conjugates. Okay, if I look in this example here, 2 divided by 4 minus the square root of 5, I have a square root here, I want to get rid of it. Well, I can't just multiply by the square root of 5, it's going to leave a radical in the denominator. So I want to multiply by its conjugate. I want to multiply by this guy's conjugate. So I got to think of the difference of squares. And remember the difference of squares is basically the same term except opposite signs. Same term but opposite signs. So what I want to multiply by is 4 plus the square root of 5. So that means I have to multiply by 4 plus the square root of 5 up top. Well, it's going to take a little bit of work. Let's do the bottom part first. 4 minus the square root of 5. If you remember our rule, this should go fast. Because difference of squares means I square the first term, 16. I square the last term, which would be 5, right? Square root of 5 times the square root of 5. And there's a minus sign in between, isn't there? And if I actually went through my FOIL here, 4 times 4 is 16. And then I got 4 times the square root of 5. And then I got a negative 4 times the square root of 5. And then I have a negative square root of 25. And if I simplify, I got 16, those cancel, minus 5. And that's what I got up there, right? Then I also have to distribute my 2 here, right? I got to take 2 times 4 and 2 times the square root of 5. Well, 2 times 4 is 8, and 2 times the square root of 5. So I'm going to write that up top. 2, oh, that's an 8. 8 plus the 2 times the square root of 5, and let's simplify this here. So 8 plus 2 times the square root of 5. 8 plus 2 times the square root of 5 over 11. And I can't simplify anything in there with this addition sign, so I just leave it. And there you go. Simplified form. So conjugates gets kind of confusing. All right, I know there's a lot of material. You might have to go back and watch through this a few times or pause and really get it to get down. But doing some work tomorrow will hopefully get it good for you. That's all we got. Deuces.